Okay, good afternoon to all. Am I audible, sir?
Yes, ma'am.
Okay, good afternoon to all. Firstly, I welcome our today's guest, Professor Rahane, sir. Today's expert lecture topic is on column theory from mechanics of structure. Before we starting the session, I will shortly introduce our today's guest, Professor Rahane AB. Sir has completed their B and Master in Structure from Amrutwani College of Engineering, Sangamner. Sir secured the rank in their batch of 2014. Sir, having the experience of 2 years in field as well as more than 6 years of teaching, Sir currently working as assistant professor in PCC. Just our guest Rahane sir.
Madam. Very good afternoon, everyone. We are here for webinar as well as expert lecture. Firstly, I would like to thank management team, Honorable Principal Sir, Honorable Head of Department of Civil Engineering from Samartha College of Engineering, Behle. Thank you for giving me opportunity to have interaction with dear students as well as with the dear faculties who are out of them. So many are my friends. Let me introduce myself within a 1 to 2 sentence only. Myself, Akshay Rahane. I have completed my master's in structural engineering from Amrutwaini College of Engineering, as well as I have completed my bachelor of engineering from Amrutwaini College of Engineering. Currently, I am working as an assistant professor in Pimpri Chinchwad College of Engineering and Research, Rave. So, dear all, today we are going to have a discussion with respect to theories of columns. Now, theories of column is nothing but your unit number 6 under subject mechanics of structure. Okay, for that we are going to have few discussions, or you may call it as few detailed study. Now what my presentation is going to have, firstly we will decide, or we will have discussion regarding what is column. Secondly, different classifications of column that we are going to discuss. Third one, how column is failing, that means failure of column we are going to discuss. Fourth one, Euler's theory for buckling of column. This is most important with respect to your SPPO syllabus point of view, as well as practical approach with respect to column. Euler's theory is very important. Next one, limitations of Euler's formula. Whatever formula is given by Euler's, for that few limitations are there that we will discuss. Next one, effective length of column. That means end conditions of column are to be studied properly before studying any type of formula. Next one, Rankine's formula. After having few limitations in Euler's formula, we are going to discuss regarding Rankine's formula for column. And last one, we will cover 1 or 2 numerical for Euler's formula as well as for Rankine formula. So let's start with the topic. Firstly, dear students, what do you mean by column? Many of you are familiar with this term column. I think all of them are from civil engineering. That means you are familiar with the word column. Column is nothing but vertical member of your frame structure. Basically, two types of structures are there. First one is load bearing structure. Second one is frame structure. In case of frame structure, we are constructing column. Column is a truly vertical member which will take load from slab and will transfer that load to the, to foundation or subsoil. That is the work of column. Now, with respect to column, we are having two different terms. First one is column and second one is strut. Now, column is a truly vertical member which is going to take a load, but strut can be inclined as well as can be vertical. Basically, strut word is applicable in case of our truss. That is the most suitable word that you are going to use. So in short, you can remember column is a vertical member of frame structure which is having function of transmitting load from the slab to the foundation. Now important term to be discussed under this, that is slenderness ratio. Now why to go for discussing this slenderness ratio term? Because slenderness, as the name suggests, it is the term related to the size and shape of column. Slender. If your column is slender at that time, according to IS 800 2007, basically 4 classifications are there. First one is slender, second one is compact, semi-compact, and plastic. But as per IS 800 2007, as well as per practicability is considered, slender are always neglected. Now, what do you mean by slender? That means your least dimensions are very less as compared to other 2 dimensions. So it is going to get failed at earlier stage. So we are going to neglect these slender sections. Now slenderness ratio. This is the term which is going to define your buckling characteristic of column. Now what is buckling characteristic? Buckling, for example, if you are going to hold any type of fan within your two fingers, at that time if you are going to apply crushing load or pushing force on both of the side, at that time it will buckle. For that we are going to see one of the GIF or one of the image in next slide. At that time it will be you will be able to understand what is buckling. Before that, what is slenderness ratio? It is denoted by lambda. It is a ratio of actual length of column to the least radius of gyration. Now actual length of column. What is actual length of column? That is nothing but distance from your slab to the another floor which is present at your floor level. That is nothing but your actual length of column. In other words, you can say height of column as well. Second, least radius of gyration. Now what is radius of gyration? Radius of gyration is nothing but distance of your point of application with respect to the axis of rotation. Now in detail we will discuss what is radius of gyration in next few slides. So from these two slides you have to remember what is column and what is importance of slenderness ratio. It is lambda, that is L upon least radius of gyration. Now column. In this image you can observe frame structure is there, thereby red shade or red portion whatever is highlighted, that is nothing but your column. Column is nothing but going to take load from the slab and will transmit that load ultimately to the footing, that is called as column. Secondly, strut. Column is always truly vertical member. Only vertical member are called as column. What is which type of load column is carrying? That is axial compression load. That is column is going to have. But in case of strut, strut is nothing but it is again a member which is going to be under compression, but it can be inclined as well. So in second image you can observe strut is an inclined member which is shown in a truss. Okay, and that is another type or another classification under axial compression member. Now, how to classify these columns? Basically, we discuss what is slenderness ratio. Slenderness ratio is nothing but effective length with respect to radius of gyration. Now, if your slenderness ratio is less than 32, at that time, that type of column is called as short column. Do remember, this term is important whenever you are going to study regarding Euler's theory as well as regarding Rankine's theory. Second one is medium column. Now, if your slenderness ratio value is in between 33 to 120, it is called as medium column. And third one is long column, where your slenderness ratio value is more than 120. So this is the classification of column based on slenderness ratio. Now slenderness ratio is going to depend on two basic parameters. First one is length of column and second one is radius of gyration. Now in diagram or image, you can see first one is tall column, which is going to get failed because of buckling. While the second one is there, which is short column, which is going to get failed and which is having attraction towards more horizontal force. So in diagram, you can see short column as well as you can see long column. Now in short, you can remember long column are having their length dimension more as compared to cross-sectional dimension. Okay, so that is nothing but your long column. Now, how column is going to get failed? Basically, column failure is most important criteria before studying anything regarding column. How it is going to fail? Any of design with respect to civil engineering is concerned with, firstly, we have to go for checking out its failure, and to avoid that failure, we are going to have provisions. Now, to study Euler's theory as well as Rankine's theory, firstly, we have to discuss failures of column. Now, what are the failures of column? First one is direct compressive stress. Second one is buckling stress. And third one is combined direct compressive and buckling stress. That means because of these three stresses, three types of failure are going to occur. First, direct compressive stress. That means in case of your short column, it is going to get failed directly. Okay, how it is going to get failed? For that, I will show you one image or one GIF file where you will come to know regarding compression failure. Imagine any of the short column is there and load you are applying continuously. Because of gradually applied load, it will get crushed. Okay, that is nothing but failure due to direct compressive stress. Second, buckling stress. In this case, your length dimension is more as compared to other two dimensions. Okay, that means because of loading, there is a possibility that your another dimension, length dimension, is going to change its position from its original axis. Therefore, buckling is possible in because of buckling stresses. Now in image you can see, here is the buckling, load is applied, okay, pulling type of force is there, or you may call it as compressive type of force is there, and because of that your original body is going to get diverted to another location, another position, and buckling is going to occur. Buckling is nothing but failure, one of the type of failure for long column. Now third type of failure is combination of your compression failure and buckling failure, which is applicable for medium columns. Now, what is buckling load? If your column is going to get failed because of buckling, first important thing is to study what is buckling load. It is the minimum axial load at which column tends to have lateral displacement or buckle. That means the point at which, or the load at which your column is started buckling, that load is noted as buckling load and denoted by PU. Okay. Now, in this GIF, you can see column is buckling, load is applied at the ends, and from its original position, it is going to get diverted to another position and buckling is going to occur. So everyone is able to see the screen, and I think they will understand what is buckling. So from original position, here is the original position, load is continuously applied and column is getting buckled. So this GIF file will help you regarding buckling failure. Now next GIF file we are going to see, that is failure of column because of crushing or compression failure, you can say. So see, yes, this is the failure type where compression is there. Sudden or instantaneous load is applied on column, and because of which material is going to get crushed. That is nothing but your compression failure. Okay. Now, in case of columns under our discussion, we may have buckling failure, you may have crushing failure, but basically we are going to avoid slender columns. Therefore, there is a possibility of combination of buckling as well as axial failure. So before going for design of column, we are going to consider two types of failures. First one is buckling failure and second one is compression failure, or you may call it as crushing type of failure. Now, if you are going to observe these images properly, you will see at the right hand side or rightmost image is showing buckled RCC column. So buckling is there, but reinforcement is there within a column. So buckling is not that much as we seen in case of steel column. So second image, second to the right, you can see buckled steel column where buckling is prominent and it is visible. But in case of RCC, because of reinforcement, you cannot observe it directly. Okay, but in case of steel members, you can observe buckling directly. Now, here is the diagrammatical representation that we are going to use whenever we are going to discuss different end conditions of Euler's formula. Now, you can see P is the load, axial load applied. It is also called as compressive load. L is the length of column. Now, because of that P load, after that minimum load condition, it is going to get buckled. Yes, and that buckle shape is shown as a black line, black dark line. That is nothing but your buckle shape. An original line is shown by dotted. So that is nothing but example regarding buckled steel column, buckled RCC column, and terminologies with respect to end conditions. Now, failure of short column. How this short column is going to get failed? For example, everyone is knowing what is stress. Stress is nothing but force per unit area. Many of the times we guys or human beings are under stress. That means load is more. As per their capacity, load is getting more. Ultimately, it is having stress. So in case of material, you can say stress is nothing but load per unit cross-sectional area. If your cross-sectional area is not capable of taking that load, at that time failure will be there. And that is nothing but your failure due to crushing or failure due to compression. So sigma or small p is equal to P upon A. P is the load applied on the column. A is the cross-sectional area. So you will get P sigma is equal to P upon A. Now next, sigma is denoted, sigma is again to be refined or defined in terms of PC upon A, where PC is crushing load, sigma C is crushing stress, and A is area of cross-section. So in case of short column, there is a chance, there is a lot of chance where your failure is due to crushing. So sigma C is equal to PC upon A is the important term to remember in case of studying short column. Now, first type of theory that we are going to study, that is Euler's theory. Euler have derived one of the imperial formula for buckling of column. Okay, now Euler have considered different assumptions. Because of these assumptions, he have derived some empirical formula. So before going for formula, it is necessary to study assumptions. So first assumption by Euler is column is initially perfectly straight and load is applied axially. Okay, so your column is truly straight. That means it is truly vertical and load is to be applied axially. This Euler's formula is not applicable for eccentrically loaded column. Okay, second one, the cross section of column is uniform throughout its length. Now cross section of column, that means its lateral dimension is uniform throughout its length. It is not tapering type of column. Its dimension is not going to get increased or decreased as per the height is considered. So your cross section is uniform throughout. This is second assumption made by Euler. Third one, column is perfectly elastic. Now what do you mean by elastic? Elastic is nothing but it is a material property by which material is going to regain its original size and shape. Material is going to regain its original size and shape. That is nothing but your elastic property. Second one is homogeneous property. What do you mean by homogeneous material? Homogeneous material, that means its properties are uniform along its dimension. In 2D dimension, if you are going to discuss. Third one is isotropic. What is isotropic? That means in third dimension as well, your all properties are going to remain constant. And last one, it obeys Hooke's law. Now, what is Hooke's law? Already you might have seen in unit 1 stress strain diagram. Okay, so within elastic limit, your stress is directly proportional to the strain. That is nothing but your Hooke's law. In short, you can remember in case of Hooke's law, as load is increased, elongation is going to occur. Okay, and it is directly proportional to load. Your elongation is increasing continuously with respect to the load. That is nothing but your Hooke's law. Hooke's law is applicable for elastic limit only. So according to the Euler's third assumption is column is perfectly elastic, it is perfectly homogeneous, it is isotropic, as well as it obeys Hooke's law. Sorry. Third one, length of column is very large as compared to lateral dimension. So ultimately Euler considered long column only. Okay, so your length is more as compared to other two dimension, breadth and width. Next one, the direct stress is very small as compared to the bending stress. That means whatever failure is going to have, it is only because of this axial load. Bending stress is more axial. Because of axial load, direct stress is less. Okay, next, column will fail by buckling alone. Now Euler have considered the theory where he considered failure of column only by buckling. We have already discussed theories of failure. First one was crushing, second one was buckling, and third one is combination. But Euler considered column failure only by third method, that is by buckling. And last one, self-weight of column is to be neglected. Now, this is the last assumption made by Euler for buckling of column where self-weight of column is neglected. So next one, effective length of column. We have already seen one of the formula where lambda was designated. Lambda is nothing but length with respect to radius of gyration. Okay, actual length upon radius of gyration. But in this case, in this Euler's formula, we are going to consider these as lambda is equal to L effective upon R minimum or K minimum, you can say. What is L effective? It is effective length of column. Now, why to go for this consideration of effective length? Because fixity conditions are important whenever studying any type of column theory. Now, what are that fixity condition? Basically, you might have studied under engineering mechanics. Three types of supports are there. First one is roller support, second one is hinge support, and third one is fixed support. Now, according to these supports, whatever condition is there in case of our column considered, according to that, your length of column, buckled length is going to get changed. Now, buckled length is to be studied. For example, both of the ends of column are fixed. For example, if you are going to consider concrete column, it is fixed at both positions. It is fixed into the slab system. It is fixed into the floor system or into the foundation system. So it is fixed column. So for that fixed column, your effective length is different. But if you are going to consider another example where pin connection is there, where hinge connection is there, what is pin connection, what is hinge connection, what is roller connection? For example, one by one, I will give you one example. For hinge connection, you can consider example of door hinge, okay, where only rotation is allowed, horizontal displacement as well as vertical displacement is not allowed. That is your hinge connection. Second one is roller. For example, for roller support, you can consider roller provided for your gates. For your college gate, for example, roller support is provided where only horizontal motion is uh, admitted or horizontal motion is possible. And third one is fixed, where no possible movement along X direction, no possible movement along Y direction, no possible movement along Z direction as well as movement is restricted. So that is nothing but your end conditions. Now, according to our length, effective length
Hello,
get varied. Yes, ma'am.
sir.
Yes, ma'am.
Sir, Rane sir,
Yes, ma'am.
your screen is stopped. Please reshare your screen, sir.
Yes, yes, ma'am. Madam, please allow me to share my screen. Ashwini, ma'am,
Yes, sir.
please allow me to share my. Yes, yes, yes.
Done,
Now,
sir. Done.
yes, yes. Sorry for interruption. Actually, it might be because of network issue or something other. It was disconnected. So we will start again from last slide. So till yet we considered these failure modes. These images we have covered. Euler's assumption we were discussing. Effective length we discussed. Now before that, before effective length, yes. So here we were. Effective length we have already discussed. According to the different end conditions, your length is going to get varied. Now that length is to be considered whenever we have to consider that slenderness ratio. Now, according to Euler's formula is there for crippling load for any type of end condition. It is nothing but pi square EI upon L effective square, where pi is constant whose value is 3.14 or 22 by 7. E is Young's modulus, or you may call it as modulus of elasticity. Now Young's modulus or modulus of elasticity, for example, for steel, it is 2 into 10 raised to 5 megapascals or 200 GPa, you can say. That value is given. Okay, I is moment of inertia. Now this moment of inertia, for that either value is given or we have to calculate it. So in case your rectangular beam is there, moment of inertia is BD cube by 12. For circular section, it is pi by 64 d raised to 4. Okay, in case of numerical, we will see that. Next one is L effective square. That is effective length of column. Now, for example, column with 5-meter length is given and end conditions are mentioned. So we have to go for calculation of effective length. So next, this is your hinge support. Example for hinge support. Here you can see roller support. Here you can see fixed support. And here are the 4 end conditions that we are going to discuss. Now, in first case, when your columns, one end is fixed and other end is truly free. एक end fixed है यानी other end truly free है. For example, you can say posting poles or light poles, which are there on your roadside. That is nothing but example for one end fixed and where effective length is to be considered as 2L. You can see this buckle shape. Now, L is the original length of column and buckle length L effective is equal to 2L. Now, second condition where both ends are pinned. That means you are going to hinge both ends. Hinge is provided at both ends. At that time, L effective is to be considered as original length of column considered. Okay, L effective is equal to L. Now, third condition, when our one end is fixed and other end is hinged. Okay, one end is fixed, other end is... Yes, ma'am?
No, sir, no, continue.
At that time, L effective is equal to 0.7 L. This is your L effective condition for one end fixed and other end pin. And last condition where both ends are to be considered fixed. For example, enforcement condition, if you are going to consider where both ends are fixed into a firm ground or firm material. At that time, that is both end fixed condition where L effective is equal to 0.5 L. That is L by 2, you can say. Okay, so these are the four end condition and I have already shown you different types of supports. Okay, so your Euler's formula is going to modify according to these effective lengths. So already we discussed what is Euler's formula. It is pi square EI upon L effective square. So when your both end are hinged, L effective is equal to L. So pi square EI upon L square is formula applicable when both ends are hinged. Second, when your one end is fixed and other end is free, or you may call it as one end is fixed and other end is cantilevered. At that time, effective length is equal to 2 times the length of column, that is LE is equal to 2L. Now third condition, when your both ends are fixed, LE is equal to L by 2. Effective length is equal to half the length. So by putting that formula, your modified formula is pi square EI upon L square. So this is Euler's formula when both ends are fixed. 4 pi square EI upon L square. When one end is fixed and other is free, Euler's formula is pi square EI upon 4L square. Now last condition, when one end is fixed and other end is hinged. At that time it is LE upon L. LE is equal to L upon root 2. That means 0.707 L. By putting that value, your formula becomes 4 pi square EI upon L square. Okay. So that were the different conditions and different modified formulas for Euler's formula. Now, whatever I is there in numerical or in formula pi square EI upon L effective square, that I is to be considered for both cases. For example, if you are going to consider Ixx and Iyy, that is moment of inertia along x-axis, moment of inertia along y-axis. But for numerical case, for our case, we have to consider minimum moment of inertia. Now that minimum moment of inertia is to be considered in case of Euler's formula. Now we will discuss different... Just one second. Limitations of Euler's formula. As I have already said, in case of assumptions, it was mentioned Euler's formula is applicable for long column. That is one of the limitation of Euler's formula. It is applicable only for long column. It is not applicable for short column. It is not applicable for medium column. There is no such a possibility that always you will get long column only. There are chances where you will get short column, medium column. So here Euler's formula fail because it is not used for short as well as for medium columns. Now second limitation, as our lambda value is going to decrease, as your lambda is going to decrease, crippling stress increases. Now what is crippling stress? Crippling is different term as compared to the buckling. Buckling is nothing but length is going to get varied directly or height parameter. But crippling is a stress which is introduced at the corners. Okay, where only shear failure is occur. That is nothing but your crippling stress. So Euler's formula, according to Euler's formula, if slenderness ratio is decreasing, crippling stress increases, and if slenderness ratio reaches 0, crippling stress reaches is infinity, and practically which is impossible. it is not possible to have maximum value of crippling stress and minimum value of slenderness ratio. So here again Euler's formula fails. Now next formula that is derived or that is needed, that is Rankine's formula. As we already discussed limitation of Euler's formula, according to Euler's it is applicable only for long column, but that empirical formula is not applicable for short as well as for medium. So Rankine derived the formula which is applicable for short column as well as for long column. As in case of Euler's formula, it was based on buckling only, but Rankine formula is applicable for both types of failure. First one is crushing, second one is buckling. So formula by Rankine is 1 upon P is equal to 1 upon PC plus 1 upon PE. Now what is 1 upon P? It is crippling load by Rankine formula. This is the value to be calculated. Now PC is crushing load. Now already we discussed sigma C is equal to PC upon A. So PC is equal to sigma C into A. Now what is sigma C? It is ultimate crushing stress. What is A? Area of cross section. What is P? Crippling load by Euler's formula. Now again here it is a combination of crushing load and Euler's formula. That means both type of failure we have considered, crushing as well as buckling. So formula is pi square EI upon L effective square. So this is the formula. 1 upon P is equal to 1 upon PC plus 1 upon PE developed by Rankine for failure. So ultimately, after solving by putting the value of PC is equal to sigma C into A and PE is equal to pi square EI upon L effective square, you will get this derivation. That means 1 upon P is equal to sigma C into A upon 1 plus sigma C into A upon pi square EI upon L effective square. By putting moment of inertia is equal to area of cross section into radius of gyration square, that means I is equal to A into K square, you will get this another equation, and ultimately modified formula is P is equal to sigma C into A upon 1 plus alpha into LE upon K bracket square, where sigma C is crushing stress, A is area of cross section, alpha is Rankine's constant, LE is effective length, and K is slenderness ratio. Now, according to the material, these alpha values are going to get varied. For example, one of the table I have shown where you will get 4 values for 4 different materials. For example, alpha for wrought iron is 1 with respect to 9,000. For cast iron, it is 1 upon 1600. For mild steel, it is 1 upon 7500. And for timber, it is 1 upon 750. Okay, so that is nothing but your Rankine's formula. So in short, I will tell you again, what is Euler's formula? It is applicable for long column, which considered formula as pi square EI upon L effective square. While second one is Rankine, who considered both type of failure. Which one first? Crushing. Second one is buckling. And his derived formula is sigma C into A upon 1 plus alpha into L effective upon K bracket square. Okay. So only here no one new term introduced, that is Rankine's constant, and which is generally given in your numerical. Okay. Which is depending on material properties. Okay. So first numerical we will discuss. If you guys are there with your calculator and notebook, you can note it down, or else I am going to share this PPT with you at the end of presentation so that you will be familiar with this as well. So here is the first numerical. Okay, first one, a solid round bar 3 meter long. That means length of solid round bar. Round bar, that means circular bar is there. Length is 3 meter and 5 centimeter in diameter. Its diameter is again given, that is 5 centimeter. Is used as a strut with both ends hinged. Fixity condition is given so that it will be easy for us to calculate L effective. Now what is asked? Determine crippling load. Take E is equal to 2 into 10 raised to 5 Newton per mm square. Okay, so how to identify it is based on Euler or Rankine? In case of Rankine, material properties alpha is always given. In case of Euler's, you will be with E, L, diameter, etc. fixity condition. So in this case, we have to use Euler's formula. So what is given data? Here is the given data. Length of column is equal to 3000 millimeter. Diameter of column is equal to 50 millimeter. Condition is both ends hinged, crippling load is to be calculated, and E is given 2 into 10 raised to 5 Newton per mm square. So which formula is to be used? Pi square EI upon L effective square. So one by one we will determine one by one term. First, calculation of moment of inertia. That is, I value is to be calculated. As I have already told you, or in numerical it is given, circular bar is there. That means moment of inertia is having formula pi by 64 d raised to 4. Okay, so pi into diameter is given. What is diameter? 50 mm. All dimensions are to be taken either in millimeters, in centimeters, or meters. Okay, so d is 50 mm. That value we have put in this formula, and you will get I as 0.306 into 10 raised to 6 mm raised to 4. If possible for any one of the student, you can check it out. I is 0.306 into 10 raised to 6 mm raised to 4. Okay. Next step, calculation of crippling load. That means direct formula is to be used, pi square EI upon L effective square. Now for L effective, what condition is given? Both ends hinged. Already we discussed, if our both ends are hinged, L effective is equal to L directly. So your formula is not going to get modified. Therefore, P is equal to pi square EI upon L effective square is equal to pi square EI upon L square directly, because L effective is equal to L pi square into E is given 2 into 10 raised to 5 into L. Oh, sorry, I we have calculated by using formula pi by 64 into d raised to 4. Okay. And lastly, L is again given 3 meter, converted it into millimeters, 3000 square. You will get crippling load as 16.11 kilonewtons. So anyone is having any doubt in this numerical? Any doubt? Yes. Okay. So this is the simple numerical which is asked generally in SPPU regarding calculation of crippling load by using Euler's formula. Okay. Now next numerical. A mild steel tube 4 meter long, 30 internal diameter and 4 thickness is used as a strut with both ends hinged. Again, L effective condition is same as that of last numerical. Find collapsing load where E is to be taken as 2.1 into 10 raised to 5 Newton per mm square. Now length of steel tube is given, diameter is given, thickness is given, fixity condition is given, crippling load or collapsing load is to be calculated, and modulus of velocity or Young's modulus is also given, that is 2.1 into 10 raised to 5 Newton per mm square. So dear students, what is given data? That I have written. So all the values I have converted in terms of millimeters. So L is 4000 mm, D is 30 mm, thickness is 4 mm, condition is both end fixed, E is given. Now calculation of external diameter is required because internal diameter is given 30 mm, thickness is given, so we have to calculate external diameter. Now whenever you are going to consider any pipe, it is having thickness throughout its periphery. So while calculation of external diameter, 2 times thickness is to be added. So capital D is equal to small d plus 2 into T. So by putting value 30 plus 2 into 4, your external diameter comes to be equals to 38 mm. So it is a type of hollow pipe, you can say, or 2 diameters are there. So moment of inertia, it is again same as that of last, pi by 64 into d raised to 4, but here 2 diameters are there, external diameter and internal diameter. So pi by 64 into 38 raised to 4 minus 30 raised to 4 upon 64. So by putting this value in your calculator, you will get value as 0.0625 into 10 raised to 6 mm raised to 4. So we have calculated I. So by using crippling load formula directly, what is crippling load formula? According to Euler's, it is pi square EI upon L effective square. Now your L effective is equal to L as both ends are hinged. So by putting value pi square, it is either 2.14 square, or directly you can put value as a pi from your calci. Then E 2.1 into 10 raised to 5, which is given. Then I we have calculated. In these numerical, I is calculated by using another formula because 2 diameters are there. But in last numerical, only single solid bar was there. Here tube is there with internal and external diameter. And last one, L effective, which is nothing but L 4000. So by putting this value, you will get crippling load P is equal to 8.096 kilonewtons. So this was second numerical with respect to Euler's theory. So I think here I will stop for my presentation. So basically it was with respect to Euler's theory numericals as well as theoretical part and formally part regarding Euler's and Rankine theory. If you guys are having any questions, kindly open your mic and you can ask. Yes, ma'am.
I think, sir, there is no question. Sir, आवाज येतोय sir?
Yes, ma'am.
So, I think there is no question. So we conclude the session, sir.
Okay.
Okay, wait, sir. Digge, sir, please continue.
Yes, ma'am. I would like to thanks Akshay sir for giving your precious time to our student development. Your efforts are really appreciable. We hope that students get their required knowledge and enjoyed this session. Once again, thanks from Civil Engineering Department, Samarth Group of Institutions, College of Engineering, and our HOD, Professor Satputhe PC. Thank you, sir.
Okay, sir. Thank you so much. I would also like to thank management as well as principal sir, head of department Satputhe sir, and coordinator dear Ashwini madam for inviting me as a expert for your session. I hope this session was helpful for students. I will share my presentation with you, ma'am. If students are inquiring for that, you can kindly submit them to directly. So thank you so much, everyone.
Okay.
Thank you so much,
Yes.
sir.
Thank you, sir.
ma'am.
Thank you.
It was a great time. Thank you, sir.
Yes, sir. Yes, sir.